In this video, I'll be teaching you guys about switches in circuit analysis. So right here, we have two models of what switches look like. First off, you have an open switch right here. So the switch, well, is open, right? You could also represent it like this, or like you kind of think of this as a gate and you can kind of flick it back and forth. And this right here is called a closed switch. So what I mean by switches is, well, anytime you have a light switch, this is an example of a switch. And maybe you've seen switches on circuits in real life, but they look basically exactly like the circuit diagram. So, what are the special traits of a switch that make it so different than other elements or other components of a circuit? Well, the thing about switches is that when you have an open switch like this, let's actually move everything down. When you have an open switch like this, and this is one here is closed, your current, so IS of W, actually let's change the color of that. So your current going through the switch, represented by IS of W, so SW is abbreviated for switch, is equal to 0 amps. And the reason why is because if your switch is open, current can't flow through, right? That makes absolutely no sense. If there's no path for the current to flow through, the current won't flow. But for the voltage at a switch, well, the voltage can still be any real number. All right? So any real number of volts. So the voltage is still possible past switches, but current, no. Vs of W. All right, what about closed switches? Well, closed switches, it's complete opposite. Your current now can be anything, but your voltage must equal 0 volts. So this right here would be Vs of W, Is of W. So the current here is 0 amps, and the voltage here is 0 volts. So you can just use basic logic to determine which is which. It's not really memorization. If the switch is open, well, then no current can flow through. So that means the current going through the switch is 0. For this problem, we want to solve both open and closed switch variations of this circuit. Now, keep in mind, every other component of the circuit, this 80 volts and these 20 ohms are the same thing. So, first things first, anytime you see a switch, you know that'll give some information. And remember, for open switches, the current is equal to 0. And in the case of this series circuit, well, since one of the currents is equal to 0, then all the other currents are equal to 0, since in a series circuit, all the currents are equivalent. Therefore, this is 0 amps and this is 0 amps. Well, if we use Ohm's law for this resistor, then we'll realize that we have 0 amps times 20 ohms, and that is equal to 0 volts. Therefore, the voltage at this resistor is 0 volts. Well, now that we know the voltage is 0 here, what can we do? Well, we can use a little bit of KVL. So KVL here makes sense because the only thing that we don't know now is the voltage of the switch. And we can use KVL to solve that based off of the voltage drops and the voltage rises. So what are the voltage rises? Well, the voltage rises are in the counterclockwise direction, the voltage of the switch, and the voltage of the resistor. And the voltage drops are V of S, or the voltage source, which is 80 volts. Well, here's the thing. We solve for the voltage at the resistor. So the voltage of the resistor was 0 volts. Therefore, the voltage of the switch, I'm going to have to go up here, the voltage of the switch is equal to 80 volts. So this right here is 80 volts. And there you go. We solve for everything. All right, how about this one? Well, remember, for closed switches now, actually we can erase this. So for closed switches, you have your voltage equal to 0 this time. So your voltage is equal to 0 in closed switches. But your current is still unknown. Well, here's the thing. we can use KVL, counterclockwise direction, and figure out the voltage, the only singular missing voltage at the resistor. So we solve for the voltage at the source, which is given, and we solve for the voltage at the switch. For the only missing voltage is at the resistor. So we can use KVL. It's very easy. You only have one missing variable. So the voltage rises, we already determined, where the voltage of the switch and the voltage of the resistor is equal to the voltage of the voltage source. And since the voltage of the switch is 0 volts, your voltage at the resistor is 80 volts. 80 volts. Well, right here we can use Ohm's law. I keep writing the M and the H mixed together. I don't know why I do that. We use Ohm's law, divide the resistance from the voltage to get current, right? So 80 divided by 20 is 4 amps. So that means this current at the resistor is 4 amps. And that means, let's actually write it up here, 4 amps. That means all the other currents are 4 amps since this is a series circuit. This problem looks a little bit intimidating, but don't you worry. I'll work through all of it once you try it out yourself, of course. So go ahead and pause the video and try this problem out. Well, now that you're back, assuming, well, hopefully you paused the video, let's go ahead and do this problem. So first thing we notice, easiest thing, the current. Bro, why am I writing volts? The current at the switch is 0 amps, right? Since the switch is open, the current is 0. All right, let's keep going on. Well, since this right here is 0, we'll notice that if we use Ohm's law, 0 amps times resistance, that means the voltage at this is also 0 volts. So nothing really electrically is going on this hold on, let me just pick a good color. This path of current. Nothing really is going on this side since there's no current and there's also no voltage. So what do we want to do? Well, let's just completely omit it. But let's not forget it, of course. So what we really have is our 60 ohm resistor left over after omitting this sort of section of the circuit. Well, once we've done that, we can combine these. These are in series, right? So if we combine these, them, we should get a singular resistor of, bro, I'm drawing this so terribly, of resistance 75 ohms, right? Because 15 plus 60 is 75. And since these resistors are in series, you can simply just add them up. Now that you have that, and you also have your voltage at the voltage source, and also this right here should be the voltage equivalent, we can solve for the current going through this circuit up here. So all we need to do is do a little bit of KVL counterclockwise, and we realize that VEQ, let's move this down actually, what I do, KVL, we notice that VEQ is equal to 100 volts. This is a rise and this is a drop, so they're just equal to each other. All right, once we've done that, we can simply use Ohm's law. So we divide the 100 volts at this resistor, 100 volts at this resistor, by the resistance 75 ohms to get 4 over 3 amps. So our ampage going through this entire series circuit is 4 over 3 amps. Therefore, our ampage going through this series circuit above is also 4 over 3 amps. And as this right here, this current is going through the 15 ohm resistor, that means that right here, I of 15 is also equal to 4 over 3 amps. And since no ampage, let's actually draw a node here. Since no amps go out of the node in this direction, and amps only go in the direction marked by these blue arrows, 160, I of 60, sorry, is also 4 over 3 amps. So if I were to work this out super logically, we use KCL at this node. We have a current I-15 going into this node, and we have two currents going out, correct? Well, we already determined that this current going to the right is 0 amps. Therefore, we only have this current going in and this current going out. And when there's only one current going in, one current going out, the currents are the same. So I-15 kind of sounds like a highway name. I-15 is equal to I-60. All right, well, now that we determined that, I know this is very cluttery, but now that we determined that, let's go ahead and find the voltages at all the resistors. Oh, forgot to state that I of S is also 4/3 amps. Since there's only one current going into this node and one current going out. All right, let's go ahead and find all the voltages now. V of 15. So how do you solve for V of 15? V of 15 is 4/3 amps times 15 ohms. Resistance times amps is equal to voltage drop, right? So 4/3 times 15 is 20 volts. So this right here is 20 volts. Okay, what about the voltage at V60? Well, let's actually erase this for more space. But V60, again, is current, 4/3 amps, times resistance. And this right here should equal 80 volts. 80 volts. Okay, looks like we solved for close to everything, but one thing. We haven't solved for the voltage of the switch. Well, what we can actually do is look past all the clutter and go counterclockwise at this loop right here, this little loop, and then do KVL. So what are the voltage drops? And which are the voltage rises? Well, V of 30 in the counterclockwise direction is a voltage rise, and V of switch is also a voltage rise. So V of switch plus V of 30 are on the same side of the KVL equation, but V of 60 is a voltage drop. Here's the thing. We solve for V of 30, it's 0 volts. Remember, since the current was 0, the voltage is 0 at this resistor. Therefore, we have 0 volts here. And we can just take this out. We can cut this out. So we get the voltage of the switch is equal to the voltage of V60. And V60 is determined to be 80 volts. Same circuit, different switch. So this switch right here is closed now. So what does this mean? Immediately it tells us that the voltage at the switch is 0 volts. But the current is now unknown. Here's the thing though. For this, it's kind of an abstract topic, but if we do KVL around here, we'll realize that V60 is equal to V30, right? Since this voltage at the switch is just 0, we completely omit that from KVL. Well, what is this? Well, this definition is a parallel circuit. If the voltages are equal to each other in resistors, you got a parallel circuit. And this kind of makes sense, right? What we have here are two nodes. Now, technically, there's a node that separates the switch and the resistor, but we can kind of think of the closed switch as just a path for the current to travel. It doesn't do anything with it. It just allows the current to travel. So what we have here is just wire along this entire thing. And the switch will count as part of the wire of our system. Well, if that was the case, we just completely omitted it, well, we would have a resistors in parallel. So what we can actually do is add these two resistors. So go ahead and find the equivalent resistance. Req for two resistors is 60 times 30 over 60 plus 30. Right? We can solve for the resistance of two resistors, the equivalent resistance of two resistors in parallel using this shortcut method where you multiply the two resistances together over the additive values of the two resistances. So this right here equals 1800 over 90, which is simply equal to 20 ohms. All right, now we know the equivalent resistance. We can redraw this circuit to make it so that we have two singular resistors where both of these resistors are combined. These parallel resistors are combined to get this guy right here. So this right now we'll call VEQ, and our REQ is simply 20 ohms. All right, now that we have this, what do? Well, as we can tell, this is a series circuit. So we can kind of treat this as a series circuit. Let's go ahead and do that. So let's bring this resistor down so we have more space at the top. Erase a little white dot, and we get V of 15 here. This is 15 ohms. Well, since we have resistors in series here, what can we do? Oh, we can just add them. So if we add these resistors, these two resistors, we just get a single equivalent resistance. That equivalent resistance is given by 15 plus 20, which is 35 ohms. And the voltage at this voltage source is 100 volts. But here's the thing about VEQ. If we use KVL around this loop here, we'll realize that 100 volts is equal to your voltage EQ. So if we have 100 volts here and we have 35 ohms, then we can divide the voltage by the amount of ohms to get 20 over 7 amps throughout this entire series circuit. Well, what's the important thing about this? Well, that means we have 20 over 7 amps throughout this entire series circuit if we step back. So we solve for the current of this circuit as 20 over 7. Ooh, that's very small. 20 over 7 amps. But if we take a step back, it's also a series circuit, so we can treat the current the same. Now that we have 20 over 7 amps, we can do a little bit more great math. So 20 over 7 amps also means that 20 over 7 amps is the current here, and 20 over 7 amps is the current here. So that means that there's a current of 20 over 7 amps going into this node in blue. Okay, well, where do we go from here? Well, right now we have current going into two different directions, so we got no clue what's going on. But we'll go forward again. Yeah, it's a lot of stepping back and forth, back and forth. But remember, we combine these two resistors to get an equivalent resistance, well, equivalent parallel resistance, which is 20 ohms. Well, let's go ahead and actually solve for the voltage here, right? And if we solve for the voltage at this resistor, we'll get the voltage of both these resistors. Remember, the voltages of parallel resistors are the same. We already determined that. V of 60 is equal to V of 30. So if we solve for the voltage of VEQ, we'll get the voltages of V60 and V30. So let's do that. So 20 over 7 amps times, let's go ahead and use Ohm's law. So 20 over 7 amps times 20 ohms is equal to, let's make more space, 400 over 7 volts. So this right here is 400 over 7 volts. Therefore, these are also, let's write that 4 better, 400 over 7 volts and 400 over 7 volts. All right, what haven't we solved? We haven't solved I60 and I30. So let's go ahead and do that. This is simple Ohm's law. All right, so Ohm's law. Let's go ahead and divide voltage. 40 over 7 volts. Oh my goodness. Let's make it smaller. 400 over 7 volts divided by 60 ohms. And once you simplify everything, you should get 20 over 21 amps. So that means I60 is 20 over 21 amps. All right, well, how about this? This voltage at this resistor here, I30. So let's go ahead. Wait, current. What am I saying? Not voltage at this resistor, current at the resistor. 400 over 7 volts over 30 ohms. And that's just equal to 40 over 21 amps. So this right here is 40 over 21 amps. Oh, I'm cramming everything. I'm sorry for those of you that have close nearsightedness. This is, wait, farsightedness. I think that's right. I don't know. I'm not an optometrist. But basically, once you solve for the current of I30, the current of the switch is also the same, since this is technically in parallel. Sorry, in series. So the switch is in series with this resistor. So 40 over 21 amps.